Hey everybody, welcome back. We're going to look at section 16.3 in the textbook today, which is electrical potential. Now before I do that, I want to take up one question from last night's homework. So I think yesterday you would have found, hopefully it was pretty straightforward. We were using the formula current is equal to quantity of charge that passes a point per unit time. I equals Q over T. Okay. We also had from the previous day that we can calculate the quantity of electric charge by using number of charges times the charge of a single elementary particle, electrons or protons, which is little e 1.602 times 10 to the negative 19th coulombs. Okay, so for question 3 it says how long, so let's just how long would it take to pass 700 coulombs of charge through a toaster if it draws 10 amps? Right, so I'm seeing 700 coulombs of charge, and I'm seeing 10 amps of current looking for time. Okay, so let's go back here. So my unknown, this is part A. Time is my unknown. We're told that we have 700 coulombs, which is the quantity of charge. And we are told that the current is 10 amps. Alright, so there's our Q and our I. So we can solve for delta T using our formula over here. I'm going to bring the delta T from the denominator up beside I and take the I down under Q. So delta T equals Q over I. Right, which in this case is going to be equal to Q was 700 coulombs divided by my current of 10 amps, and I'm getting time is 70 seconds. It's going to take a minute and a bit for that much charge to go through this toaster. Okay, the B part of the question says how many electrons pass through the toaster during this time. So I'm now looking for how many electrons. I'm looking for big N, the number of charges. So I'm going to go back to my solution here, and for part B, the question is how many charges go through the... So to use N, I need to know big Q, and I need to know little e. Well, little e is a constant, 1.602 times 10 to the negative 19. Q, oh, that was given right here, 700 coulombs. Pretty messy, but it is 700 coulombs. So N is going to be equal to quantity of charge divided by the elementary charge, which in this case is 700 coulombs divided by 1.602 times 10 to the negative 19th coulombs per electron, and I'm going to get an answer. I'm just going to do this on my calculator here. I'm getting 4.37 times 10 to the 21. Electrons. Okay, so there's our first two formulas, and again, just try and keep them handy. I wonder if I go back and pull up my formula sheet here. If I'm looking at electricity and magnetism, so we've now used this one here. I equals Q over T. Current is quantity of charge divided by time. I don't know why it's not a capital Q. down here we've used Q is equal to N times E. We just use those two formulas for today's class. We're just going to keep building as we work through all of these formulas here. All right, so let's go back to today's note. We'll pick up where we left off yesterday with section 16.3 on electrical potential. Now, that word potential, right, is potential energy. So we're talking about a form of energy here, which is the energy carried by electrons. Now, the reason why electrons have energy is based upon the amount of repulsion that there is. So just like the higher an object gets from the surface of the Earth, the more gravitational energy it is, the more electrons are pushed together, the more they want to push apart. They have energy stored up with them in that force of repulsion and or attraction, depending on what we're talking about. So what happens here is we can give electrons more potential energy if we squeeze them closer together. So what happens at a source, right, the source is where the electrons get their energy from, is the electrons get squeezed together, and that gives them their electric potential energy. Now, once they get to the load, what's going to use the energy, that energy from the electrons will get transformed into some other type of energy, and what we're going to do here is similar to what we would have done in gravitational energy, was to figure out how much gravitational energy an object has. I figure out how high it is at one level, how high it is at the second level, and I compare the two gravitational energies to represent the amount of energy change that the object has. In this case, we're going to do a similar thing. We're going to measure the energy of electrons at one point in the circuit, and then we're going to compare it to the energy of the electrons at a different point in the circuit. So what I need now are two separate measurements of electrical potential energy, and then I need to compare those two numbers. So unlike my current, where I just plunk my ammeter into the circuit and then it counts how many electrons go by it, now I need to attach my my voltmeter, which is going to measure electrical potential. I'm going to check the voltage at one point and the voltage at another and see if how it's any different. Okay, so I'm going to measure the difference in potential. Now, another word that we use to describe electrical potential difference is the word voltage. And the reason for that is because the units are measured for electrical potential difference are measured in volts, named after Volta, an Italian physicist. So what does potential difference tell me? It tells me for any coulomb of electrons, how much electrical energy are they carrying, right? What is the quantity of electrical energy in joules carried by a coulomb of electrons? Okay, so my answer now is going to be in joules per coulomb. It's going to be measured in joules per coulomb because I'm measuring joules divided by coulombs here, and joules per coulomb are called volts. So if I've got electrons that are 1.5 volts, that means a coulomb of electrons has 1.5 joules of energy. If I have electrons that are 9 volts, a coulomb of electrons carries 9 joules of energy. So I'm comparing how much energy different electrons are carrying, based upon a standard number of electrons, which is the coulomb, and the amount of energy, just like we've been doing all through this course, measured in joules. Okay, so we know that a coulomb is our standard unit of charge. It's a quantity of electric charge. Right? And we're going to measure our voltage or electrical potential difference using a voltmeter. And to do that, I need to compare two separate places in my circuit and then see how the potential is different in those two places. So because of that, I'm going to have to set up my circuit in parallel. Now again, I should probably take a minute and review the whole notion of series and parallel. So let's just go back to our whiteboard here. Okay, and if I look at series versus parallel, if I've got a battery here, and I'm going to put a bulb here, I should probably put a switch in here. There's my bulb. Okay, there's my single bulb. If I wanted to put a second bulb in, I could put a second bulb in. Now I have one bulb and two bulbs. I could also set it up in a configuration like this, where as electrons leave, again, remember this is the negative side, this is the positive side. We know electrons are going to leave, so they're going to come out of here, they're going to zip around the circuit, go through the bulb. When I close the switch, so the switch is open right now, it's easier to see when it's open, but when I close the switch, electrons are going to fire around the circuit and be attracted to the positive terminal of the battery. Notice it's a battery because it contains two cells. That was our definition from yesterday. A battery is whenever I have two or more cells together side by side, in series actually. Now if I take that second, so notice that for this first circuit here, electrons only have one path that they can choose in, that they can flow through. So that's called a series circuit because electrons don't have any options. They can only get from the beginning of the circuit here to the end of the circuit here by traveling along one path. The same thing with circuit number 2. Even though there are two bulbs that the electrons have to go through, they really have only one path. They're going to leave the source, go through bulb A, go through bulb B, go through the switch, and then go back. They don't have any choice, right? They've only got one possible set of options. But if I look at the third circuit here, electrons are going to leave the negative of the battery, and they're going to get to this point right here where they're going to have an option. They can go through bulb A or they can go through bulb B. If they go through bulb A, as they travel, as they travel along here and go through bulb A and get to the other side, right, they're going to go back to the battery. Okay, so there's my first possibility. There's also a possibility that electrons can go this way instead of going through bulb A, and they will go through the second bulb. They will get to the junction here. When they get to the junction, they're going to meet electrons that were coming from the first line, from that A bulb. So because there's electrons coming that have come through the A bulb, the ones that went through the B bulb here, the ones that went through the B bulb don't have a chance to go back up the line towards A because there's current flowing down A, and the B electrons, which are negative, are going to be attracted to the positive battery here. So they're not going to want to go back up that A line. They can only go in one direction. Right? So I've got the possibility of that first line or this second line, and because electrons have those two possibilities, this is my parallel circuit. And this was my series circuit. Now, notice that if I wanted to measure current in this circuit now, so let's go back to, let's get rid of these arrows from here. If I wanted to figure out how fast electrons were traveling through here, I could put an ammeter anywhere, and we did this yesterday, anywhere in the circuit, and it will measure the speed. So let's just take this piece out here and let's put an ammeter in there. So I'm going to put my ammeter right here to measure how fast electrons are going to the bulb. Okay, so the ammeter is in series. I still haven't given electrons another option. They have to go through the path, through the bulb, through the switch, through the ammeter, and down to the back to the battery. Now let's say I wanted to measure the voltage in this system. Okay, let's say I want to compare, to measure voltage, if I put my voltmeter and compared this point to this point here and said, how much voltage is there? Well, again, remember what I'm doing is I'm comparing the electrons at this point here with the electrons at this point here. Well, they should be the same, right? There should be no difference in electrical energy, because the place where electrons are going to use their energy is when they get to the bulb over here. So comparing the voltage there, if I actually took a voltage reading there, it would say there is no difference between the electrons on the left side there and on the right side. But notice that I've had to put the voltmeter in parallel. Now, even though electrons, what we're doing here is we're comparing the potential on both sides, so it's being set up in parallel. I'm not really giving the electrons that extra route to go through. I'm just setting it up as if electrons have another possible route. And that's how our voltmeter is set up in parallel. So if I took my voltmeter now, let me get rid of my series circuit. Let's take my voltmeter and I'm going to connect it on either side of that bulb. Now, if these are 1.5 volt cells, that means my voltage should be 3 volts. So if I measure the voltage, comparing the volts here on this side to the voltage on this side up at the top here, what should happen is electrons that leave the battery from here come fully loaded with energy. They flow along carrying their energy till they get to the bulb, dump their energy, then go back to the battery empty. That's the whole notion of an electric circuit, is electrons leave the source loaded, electrons go back to the source at the end empty. They have to. They can't have any energy left when they get back to the source. So if I check the voltage here on either side of the bulb, I should find that the electrons had 3 volts down at the bottom, had 0 volts up at the top. So if I compare the two, the difference in voltage is 3 volts because they've used all of their energy. If I was to have my voltmeter here and check one side of the battery to the other side of the battery, again, notice that when they leave the battery here, they're fully loaded, 3 volts, and when they get back to this end, they have 0 volts. So the voltmeter should compare a 3 volt to a 0 volt. 3 minus 0 gives me a voltage reading of 3 volts. All right, so voltage is energy carried by electrons. It's not perfect to describe them this way, but I like to say there are 3 volt electrons, there are 1.5 volt electrons, there are 9 volt electrons. Now really it's a coulomb that's carrying that potential energy, but I like to use voltage to represent the amount of energy that electrons are carrying. Okay, so there's our quick refresher on series and parallel circuits. Okay, let's go back to our note. So, like I said before, your voltmeter has to be set up in parallel, and we have to set it up on either side of a source or a load to measure the amount of potential difference on either side of that source or load. Okay, so there's 2 samples in the textbook on page 549. Okay, so let's go back to our whiteboard. Okay, so page 549, sample number 4 says, what is the potential difference across an air conditioner if 72 coulombs of charge transfer 8.5 times 10 to the third joules of energy? So this is example 4. And we're told that we have 72 coulombs of charge. That is Q, that's the quantity of charge. And we're told the amount of energy being transferred is 8.5 times 10 to the third joules. And I'm looking for what is the potential difference, or voltage. So voltage is equal to the energy carried by electrons divided by the number of charges or electrons. So if I substitute in now, I get 8.5 times 10 to the power of 3 divided by my 72 coulombs. And I'm getting 1.2 times 10 to the 2 volts. So if I compare the electrons going into the air conditioner to electrons leaving the air conditioner, they have given up that much energy when that many electrons go through them, and that's what the voltage is for that particular air conditioner. Example number 5, which is just below it, this is on page 549 in our textbook. This is example 5. It says a static electric shock, so again, delivered to a student from a friend, transfers 1.5 times 10 to the 1 joules of electric energy. Okay, so we're told the electric energy is 1.5 times 10 to the 1 joules, right, which is 15 joules. And it says the potential difference is 500 volts. And the question is, what quantity of charge moved in that spark? Right? How much charge moved from the person A to person B in that spark? Now again, if I know that voltage is equal to energy divided by the quantity of charge, I'm just going to take the Q up to the V and the V down back where the Q was. And I get, oops, cancel. And I get Q is equal to E over V. Okay, so I'm going to take my 1.5 times 10 to the 1 joules divided by my 500 volts, and my quantity of charge is going to be 0.03 coulombs of charge, or electrons, are what jumped in that spark. All right, so our textbook does a good job of talking about. There's a real nice picture. I can't actually take it off my out of my textbook right now, and it's really difficult for me to find bits in the textbook. But if you look in the textbook on page 550, you'll see a picture that shows. I'll draw the sketch of it. Shows a factory where trucks are picking up a load from a conveyor belt. So here's a truck coming along. Oops. And it's traveling along okay, and what's happening is the truck is getting loaded up here with stuff that it's going to carry. It's going to carry those things till it gets to a site where it's going to deliver them. And then at the other site, it's going to deliver the load, and then it's going to come back empty to pick up another load. And there's our electrons, right? Electrons are picking up energy on this side, delivering the energy on the other side. And in order to keep this going, I can't stop the trucks from moving. All right, so if between this truck here and this truck here, I had 10 other trucks, right? All of them have to be moving one behind the other. If anyone stops for some reason, it stops everything. So it can't happen. For electrons don't break down. They will continue to flow. Now, so we've got our two formulas then. We have our two formulas. V is equal to E over Q, and Q is equal to I over T. Sorry, I is equal to Q over T. So if I know that voltage is equal to energy over charge, or energy equals VQ, and I know that I is equal to Q times delta T, which means, if I rearrange it, Q equals I delta T. If I take this value for Q here and substitute it in there, then I can take I delta T and substitute it in up there, and I get E is equal to VI delta T then. And that's our last formula for today. Right? E is equal to VI delta T. All that formula is a combination of the two formulas that we've already developed in today's note and in yesterday's note. Right? So let's very quickly look at samples 6 and 7. So note what I can do here is I can determine how much energy is being transferred if I know the voltage of the electrons, of potential difference between 2 points, the current, how fast they're moving, and the longer they get there, the longer they have to deliver energy. Notice it doesn't have a Q in here because I've replaced the Q with I delta T. All right, so let's go back to page 550. Page 550 says a 1.5 volt AA battery is running an MP3 player. No one has MP3 players. This textbook is dating itself. Drawing 5.7 times 10 to the minus 3 amps of current for 6 hours, and then it runs out of energy. How much energy did the battery transfer? All right, so this is example 6 on page 550, example for question 6. So we're told we have a 1.5 volt battery, and that it's going to run for 6 hours. Oops. And it's going to have a current, in other words, how fast electrons are moving through it, of 5.7 times 10 to the minus 3 amps. And the question is, how much energy did that battery deliver before the battery died? In other words, how much was stored in that battery when I got it? So we're going to use that formula that we just developed. Energy is equal to voltage times current times time. Okay, so I know my voltage. It's 1.5 volts times a current of 5.7 times 10 to the minus 3 amps. And we're told the time is in hours. I need to convert the hours into seconds. I know 3,600 seconds is 1 hour. So my hours can cancel. And I'm getting 21,600 seconds. So I'm going to put that number in here for my time, 21,600. And what I end up with is 185 joules of energy. When you buy that battery at the store, okay, it comes hopefully fully loaded. Right? That means it's got the maximum amount of energy. Right? That energy is chemical potential energy stored up inside the battery. Right? What's going to happen is that chemical energy is going to deliver its energy to electrons. The electrons are going to now carry that energy as electrical potential energy out of the battery and spend it running the MP3 player, then go back to the battery empty and pick up more energy. And they'll continue doing that until all of the chemical energy is gone and there's nothing left to charge electrons, right? And the amount of energy was at 185 joules. If I move up to example 7 on the same page, on the next page, okay, I'm on page 551. It says a coffee maker draws 5 amps of current for 270 seconds and it uses 1.6 times 10 to the 5 joules of energy. What is the potential difference across the coffee maker? In other words, if I compare the potential on one side of the coffee maker and on the other, right, how much energy have the electrons lost? Okay, so I know that there's 5 amps of current. There's my current. We're told the time that it's going to take to make the coffee is 270 seconds, and that the energy delivered, or that would be required, again, if you did MC delta T, you could figure out, and you know how much water there is, you could find out how much energy was required. And that energy that's going to be delivered is 1.6 times 10 to the 5 joules. Okay, and the question is, what is the potential difference? Now, if my formula says E is equal to V I delta T, I could solve for V by taking the I delta T from this side down to the denominator. So V will be equal to E over I delta T. Right? So now let's substitute in. Energy is 1.6 times 10 to the power of 5 joules divided by my current, 5 amps, times the time that it took to make the coffee in the coffee maker, which is 270 seconds. I'm getting an answer of 119 volts. All right, so that's using E is equal to VI delta T. So let's go back to our note. So that's samples 6 and 7 from page 570. I'm going to leave you with these 3 questions here and then about a dozen questions here on page 575. Right. And then I'm going to finish there. So tomorrow when we come back, I'll take up 1 or 2 of the questions again. And then I'm going to leave you with electrical resistance and Ohm's law, 16.5, ahead of the lab that we're going to do, which will be our last lab. Our last gizmo. It's actually not a gizmo. It's